Okay, guys, well, welcome back. This is 3H, and it's talking about powers and roots of complex numbers. There are two examples which I'm going to go through here before we get to the exercise, but there's a nice little investigation to start off with, which just gets you to work out what is I to the power of 0, I to the power of 1, I to the power of 2, and so on. It is worth just stopping and thinking about that, trying to write yourself a list, because that's going to turn up when we do expansions of binomial expansions, or using the binomial theorem with complex numbers to the power of n. Okay, so let's have a little, I don't want that. Okay, so I've just set this one up on the side here. Now, I to the 0, as with everything, everything to the power of 0 is going to be equal to 1. Okay, and I to the 1 is just I. And I squared we know is minus 1. So that's, of course, minus 1 is I. Square root of minus 1 is I. And when we square that, we're going to bring it back to minus 1. Okay, now when we do minus 1 times by I again, we'll get minus I. And then I to the power of 4 is now saying, well, let's times this thing by doing this times by I. Well, now we know that I times by I gives us minus 1. So minus 1 times by the minus 1 essentially on the front brings us back to plus 1. And then you can see what's going to happen. We're going to circle around those numbers there. They're all going to turn up again, of course. So when we times 1 by I, that's the same as doing 1 by I here. So we're going to get the same set of numbers as we increase here. Okay, so you should be aware of that pattern. Of course, you can get them out using your calculator. You should be aware of the pattern there. You should be able to develop that pretty swiftly. Okay, they don't give you a little rule or anything. Okay, they do mention that we're talking about z to the 4 conjugate and conjugate of z to the power of 4. And what do you notice? So the investigation is nice, but we'll see that through the next question as well. Okay, so let's look at the question. It says, can we work out z to the power of 3? So here we go, this is z. So we're going to do 2 plus I to the power of 3, and we can use our binomial expansion, binomial theorem, to multiply this out. So we've got 2 cubed, 2 squared, 2 to the 1 and 2 to the 0, and we've got I cubed and I squared and I to the 1 and I to the 0 here, which can disappear, of course. And we need to put in our coefficients of each of these terms from Pascal's triangle. So you should know that the third line, or potentially fourth line, of Pascal's triangle gives us out our NCR coefficients, which we've discussed before, of course, of 1, 3, 3, and 1. So it should put the 3 there, the 3 there, and the 1. And the 1 is not really necessary because it's just holding that term. It's just the identity function, of course. So let's put all this together. And when we put it together, we're getting out 8 and 12i, and we're getting 3 times 2, so we're getting 6i squared. So then minus 6 there, because I squared, of course, is minus 1. And then we're getting I cubed on the end there as well, and I cubed is equal to minus I. So we can simplify this one in the end to give us 2 plus 11i. Now, since I've been busy making little mistakes on the next one, I'll spare you the binomial expansion, but the binomial expansion, which I've just made, is this one here. There's nothing wrong with this. We are saying for the conjugate of z, there we go, there's the conjugate of z in this question. Part B, conjugate of z is 2 minus I. We're doing this to the power of 5. And we're using a binomial expansion here. And I've just drawn out Pascal's triangle in order to use all of our NCR terms, which come out in that final, in the 5th row there, in this row in Pascal's triangle, the one with 5. So in order to make that expansion, again, what did we do? Let's have a little look. I've done 2 to the power of 5 to the power of 4 to the power of 3 squared, 2, and I didn't really leave myself a lot of room here, and then 2 to the power of 0 at the end. And then the other way round, so starting with our sixth term here, we've got I to the power of minus 5, I to the power of 4, I cubed, I minus I squared, minus I, sorry, it's minus I in all of these brackets here, and minus I to the power of 0 at the end. So just ascending powers of minus I as we go up there. And make sure, of course, that you're putting minus I in brackets. Okay, and then we came up with our coefficients. It's always plus in between all of these things because we're looking at the standard model doing a plus b to the power of n. And then we're putting in our coefficients from Pascal's triangle, and you can see I've put in 1, 5, 10, 10, 5, and 1 there. The ones I've just kind of neglected to write. Okay, so that's what's happened there. I know it's looking a little messy, and I really didn't give myself enough room. This is absolutely classic, but obviously try and give yourself enough room when you're doing it as well. Okay, so after this, it's actually fairly tricky to get it right when you're doing things like minus I to the power of 5. Okay, because that involves both minus 1 to the power of 5 and I to the power of 5, and I to the power of 5 comes from this little list over here, which we made at the start. Okay, so we've got the two parts here because we've split up minus I into its two factors, minus 1 times I, and then we've used our laws of indices there to apply power 5 onto both of those parts. So now we'll have to do that in each of these cases, like a little bit of working out aside. The first one is obviously straightforward, so that's just plus 32. The next one is 2 to the power of 4, 16 times by 5, which is 80. And we've got times by minus I, so that one's actually easy. And then it starts to become a little bit more complicated, so I'll do minus I squared. So I'm going to split that up into the two parts. I'm going to say we've got minus 1 squared and I squared. Now I squared is just equal to minus 1. And minus 1 squared is plus 1. So the answer to that is going to be minus 1. Okay, so the answer to this thing here is going to give us out minus 1. We have to do a little bit of working out to get that. So this is going to give us minus 1 now. And in the front here, we can see that we've got coefficient of 80. So 2 cubed is 8 times by 10 is 80. Now you'll notice that these terms are going real, imaginary, and so on. Okay, but now let's look at the next one though. So we're now looking at this one here. And again, I'm going to unpack this thing here, minus I to the power of 3. So we've got minus 1 and I both raised to the power of 3. Now, minus 1 to the power of 3 is minus 1, which is just minus. And I to the power of 3, we can see from over here, is minus I. So we're going to get out here plus I. Okay, so this is plus I. So we're getting a plus here and an I. And we need our coefficient as well. And our coefficient in this case is 40. Okay, 2 squared times by 10 is 40. Okay, next part, we've got I minus 1 to the power of 4 and I to the power of 4. Now, I to the power of 4 is 1. So we can write 1 here. So we've just got that from this table over here. And minus 1 to the power of 4 is also plus 1. So this is just going to give us plus 1. So we're just going to have plus here and then our term that we're getting at. So plus, in this case, our coefficient, which is 10. Okay, so next term here, we're getting, for this one, we're getting out I minus 1 to the power of 5 and I to the power of 5. So that's again just splitting up this term at the end. So to see what we're adding on at the end. So we can see we're getting minus 1 from that. And I to the power of 5 is back to I again. So we're getting minus I on the end. Okay, so It's worth trying to do that yourself, in fact. It may be easier to try and figure it through yourself than to listen, in fact, to me going through each of those steps. But that's what you should get. And so now you're saying getting 32 minus the 80 and then plus the 10. So that's bringing us to minus 38 there. And then we're getting the imaginary terms that we need to bring together. So that's these ones here. So we've got minus 80 plus 40 brings us to minus 40, and then minus I brings us to minus 41I. Let's just check that we got that one right. Yeah, we've got minus 38 and then minus 41I there. So that one's correct. Okay, but it's quite fiddly to get that one right, and there's a lot of opportunity for you to make errors there. So I really suggest that you either take lots of lines of working out or do lots of little working out aside, which is really clear. I know I've deleted a lot of mine, but yeah, just take this as slowly as possible through these steps to make sure that you're getting it right. Okay, now I'm not going to do part C, but part C is basically the same as part B, apart from they switched around the conjugate and the 5. So they've switched around these two things here. So we've got the two powers being swapped around. And the point of this is to say, well, are these two things the same? Can we, if we've got z to the, the conjugate of z to the power of n, is that the same as z to the n conjugate? Okay, and that's what they're asking. Now you can do a very, very similar process and you'll find out that it is the same. You can also check on your calculator that it's the same. And I think in the investigation, they said, what do you notice when you do z to the 4 conjugate and take the conjugate of that, or when you do the conjugate of z and then raise that to the power of 4? So, and that's in part 7 from the investigation. Now, both in part 7 from the investigation and from this example 19, you should notice that you get the same thing. Now, that's not a proof of the fact that we've got this statement here, conjugate of z to the power of n is z to the n, all conjugated. So it's not a proof of this thing here, and we can prove it quite easily later on when we use a different form other than the Cartesian form for writing complex numbers. But for the moment, we've just verified that it's true using a couple of examples. And you can verify it's true with many other examples, of course. But we've not actually made a proof of this just yet. But we can make a proof of that quite easily later on. Okay. So let's look at example 20 now. And this one says, evaluate the square root of this complex number. So the technique which we're going to use for this one is to say, well, let's let this equal to a complex answer. So let's let this equal to z. But z, of course, we can say is equal to a plus bi. So we're going to set it equal to that. Now we've got 7 minus 24i is equal to a plus bi, this generic complex number. Now we're going to square both sides. So normal kind of algebra from here on in. So we've got 7 minus 24i equals to the square of this thing here. So we're now getting a squared plus 2ab lots of I, and then minus b squared on the end as well. So we're getting bi times by bi, which of course is giving us minus b squared. So the I times I is giving us the minus 1. Okay, so once we've got that, we could then compare both of the sides that we have, and we can say, well, let's look at our real amounts on each side, and let's look at the imaginary amounts on each side. So on the left-hand side, we can see that we have 7 as our real as the real amount of this complex number, and on the right-hand side, we can see that we're getting a squared and b squared, which don't involve I. So they're the real parts of this. Now, when we're coming up with an expression is equal to an expression here, in fact, this is an identity because we're setting this up to say, of this is identically equal to our answer, which we're going to get out. So we could actually say that this is identical to. So we're saying, firstly, that our real amounts should be the same on both sides, but also our complex amounts should be the same on both sides. So what we were talking about before, if you have a complex number and another complex number, then their position on the Argand diagram should be the same if they are the same complex number. Okay, so we can say, come up with two equations. We can say 7 equals a squared plus b squared, and then we can say that minus 24 is equal to the plus 2ab here. Look, plus 2ab. And now we've got a set of simultaneous equations which we need to solve. So it's your choice, really, how you're going to go about solving those. And I suggest, again, it's perhaps nice to stop here and then actually have a go at this yourself. So let's take it a bit further forwards. We could substitute one into the other. Perhaps let's say that we could get a rearrangement of this and put it into this so that we're not ending up with any square roots. So let's rearrange the imaginary equation which we're getting out here. And so we can say that a, for example, is equal to minus 24 divided by 2b, which is equal to minus 12 over b. Now we can substitute that one in where we see a on over here on the other equation. And I'd probably say to the examiner what I'm doing at that point. I might actually say sub a is equal to minus 12 over b into, I might call this 1, call this 2, and say sub it into 1. Okay, but since I've not got a lot of space on here, I'm just going to go straight for it. Okay, so I'm going to say now 7 is equal to minus 12 over b, that's squared, plus the b squared. Then we can multiply that out, of course, so we're getting 144 over b squared plus b squared equals to 7 still. And then we can times everything by our denominator here, and we'll get 7 equals 7b squared equals to 144 plus b to the power of 4. Okay, well, if you want, you could call this 7x equals 144 plus x squared by letting b squared, letting x equals b squared. So you can solve a quadratic here. And so we can see we've actually got a quartic, but it's in the form of a quadratic. For myself, I'm not going to actually do that. So you can do it like that, and then you can solve x equals b squared. So once you get your two answers for x, we can then solve for b. Okay, but in fact, I'm going to do it all in one here. So I'm going to take the b to the 4, leave on this side, and I'm going to take the 7 minus b squared over to here, and I've got plus 144. And now I need to find two factors that make that work, and hopefully that's we're able to factorize that. Now, just to spare a little time here, because listening to me think is painful, we can see that the two solutions to that are 9 and 16. Okay, so we're getting 9 and 16. You can see that they had the same equation when we were putting in for a squared as well. So they have this whole thing in terms of a squared, but because of the symmetry in these two equations, you'll get a same expression out for b. You're ending up with the same expression in terms of a as well. So that's kind of a coincidence there. So we're getting 9 and we're getting 16. So we're getting minus 16 plus 9 there. Our two factors in the brackets there. And so we can see that we're getting out b is equal to minus 9 and equal to plus 16. Oh, sorry, missing something. That's b squared. That's b squared. Now, b squared equaling to 9. Now, remember that b is set up here not to be a complex number. So you might be thinking at this stage, oh, well, hang on a second, b is equal to the square root of 9. That's fine, we're working with complex numbers here. So b is equal to 3i. Okay, that's by me separating this out to minus 1 and square root of minus 1 and square root of 9. Square root of 9 is 3, this is I. Okay, well, you might be thinking that is fine for b, but of course, b wasn't set up to be a complex number in the first place. It was set up to be a real number, a real coefficient, which is the imaginary part when we combine it with I. So you can't have b being equal to minus 3i in this case. So this is not going to give us a solution. We're only going to get the solution in this case by doing b squared is equal to 16. And so you're getting b is equal to plus or minus 4. Okay, now if we substitute plus or minus 4 into here, so if we say b is equal to 4, for example, we'll end up getting a is equal to minus 12 over 4, which is equal to 3. And of course, if b is equal to minus 4, we can use this equation again for a, and we can see that we're getting out a is equal to 3. So, in other words, we're getting now for z two combinations. So our z, which we set up like this, is going to give us either from the second one, which we're seeing here, we're getting 3 minus 4i. From the first one, which we're seeing here, we can see we're getting minus 3 and plus 4i. So those are the two final solutions which we have here. Remember, it was important that we couldn't include the square root of minus 9 because b was not a complex number. B was set up to be a real number. Okay, so there we go. There's our two solutions in this case. And what you might notice here is the solutions come in pairs. We're both getting 3 minus 4i and the negative of that. Now, that's quite important because when you do this on your calculator, you're only going to get one of those solutions. So to get the other solution, you'll have to remember to take minus that answer if you're purely doing this on your calculator. Right, okay, and we'll leave this one there because that's as far as this is going in the book, and that's exactly what they're saying in the book there, which will give you access to this next exercise. Now, when we're playing around with roots with complex numbers, later on, we've also got different methods for questions with roots when we use a different form. At the moment, we're using a Cartesian form, but later on, we can use a different form for complex numbers, and we'll talk about that when we get to it later on. Okay, so there we go. Those were the two solutions there. There we go. That's evaluating the square root of a complex number by setting it up as a complex number and then just working through the algebra there. Okay, so thanks for listening to that. You have enough skills now to do 3H, and 3H takes you up to question 6. Next time round, we're dealing with polynomial equations and inequalities with complex numbers. Okay, thanks for listening, and I'll see you for the next one.